All right. Oops, sorry. Today we'll continue on from last Thursday, where we talked about the concept of how do we represent data in the memory, right? And how does the program understand the data that you're writing? Mm, this can be in form of integer. This can be in the form of uh, different formatting, right? And today we will follow on and talk about the other side of your code. That's actually the important side of your code, which is the program itself. And how do we represent them, right? So that it runs on your computer. So a quick recap from last Thursday, we talk about data representation and we follow with bit manipulation. Um, the assignment 3 will One of the big focus on assignment 3 will be on the bit manipulation. The other focus will be on the today lecture, which is how do we represent a program. For the bit manipulation, we left with the question that say, hey, let's say I have an array of integer, and each integer has its pair. And there's one integer in the array that, for some unlucky chance, that integer doesn't have a pair. It's the only single integer in the array. So how do I find that integer? Can someone tell me what can I do to find that integer? How do I write a program to identify that one single integer that doesn't have a pair in my array? So let me give you an example. Let's say I have an array that has an integer value a, b, c, a, b. How do I identify that the value c in this case doesn't have a pair? Can I use nested loop to do this? Can I use a nested loop where the first loop would iterate for every single element? I'll seek through everything in this array and see if there's a pair, if there's a matching value. Can I do that? The answer is yes, you can. Well, the complexity of this approach, right? Yes. So if you can keep the record of what you've looped over, you can definitely do this. And I like the comment because it actually has some certain overhead where you have to loop twice, as in like for each iteration of the first loop, you have to loop over every element. So it's n square, right? Can I do the same task using XOR? Actually, can I have the algorithm that goes through this array once and somehow you find C? The answer to that lies in this operation XOR. It just happened that if you have A XOR A, you are going to get 0. Why? Let's say A is some binary value, right? And I am going to XOR the same thing. When you want to work through XOR, the way it works is I have bit, the first bit XOR with the second bit. If both of them have the same value, if both of them are 0, you're going to get 0. If both of them are 1, you are also getting, you're going to get 0 as well. The only time the XOR operation, and the reason why they are called XOR is it's the exclusive OR. It's almost like an OR operation, but it's exclusive, which means that only one of them has to be true in order to make it true. If both of them are true, it's become false. So the only case where XOR results in a 1 is when the two bits are different. So if I have something like this, I XOR them, what do I get? And someone tell me, what do I get if I XOR this same number? 0, right? So A XOR A is 0. So what I can do is I will start with, let's say, temp, right, equals 0. And then I'm gonna XOR temp with every single element in this array. What am I gonna get? So if I XOR everything here together, I do this. Oops, sorry. I do A XOR B XOR C XOR A XOR B. What am I gonna get? The A would get 0. Basically, A XOR A becomes 0. B XOR B is gonna become 0. C XOR 0 is gonna be C. So from this, I can just loop through every single element in my array, XOR everything up. You will then left with only that one integer that doesn't have a pair. Any questions about this? So this is kind of like a nice trick, right? It doesn't actually have the implication of real program. I mean, there might, right? You might have to identify certain unique elements in an array. But my point is that operations on complex data, sometimes there are tricks that you can do in terms of logical operation, which we'll cover this more in assignment 3 that is coming up, that you can make the operation faster through just AND or XOR, NOT, and many other series of logical operations. And this actually becomes a common thing when you want to optimize your code, because these logical operation is really fast compared to adding and multiplying. All right, so let's move on to the next concepts that we have to learn for this class. How to represent a program, right? Because we cover how to write program in C, we cover, other class cover how to write program in Python. We also covered that the GCC, the compiler, would compile your C code into something the computer understands. The first thing I want to do is a quick recap on what is a computer, right? So the computer is basically, you have the processor, the CPU that you buy, right? The memory, the memory that you plug onto the motherboard. Anyone here built your own computer before? Anyone here has a desktop and help building that, or you buy parts and put it on a desktop? So where does the memory go to? Let's say you go to a coffee, not coffee shop. Sorry, I think I crave coffee. That coffee. When you go to the computer shop, right, and buy the memory, that memory stick that you buy, it's actually called DIMM. Let's say you buy the memory DIMM, DIMM. Where do you plug it into? Where does it go in your computer? All right, for those of you who built a computer before, there's someone do a thumbs up earlier. Where do I put the memory in? The main board, yes. So basically, the main board is where you put the memory in. You also put the CPU on the main board, right? Basically, the main board is where you connect everything together. So the processor would talk to the memory, and then the memory kind of talk to the I/O, like hard disk, network drive, monitor, the speaker, and mouse and keyboard, right? And the way the program process this is both the program and the data would be stored in the memory. The processor would kind of look at the program in the memory and then run the program. So now you might have a lot of questions that say, hey, I know the program is there, but how does it actually get run? How does it know what to do? So to answer, that was my cat that meowing really loudly. Sorry, I got distracted. So to actually know how does the computer actually understand what it is supposed to do, this has to be governed by this terminology we call instruction set architecture. Anyone heard about this word, x86 assembly? Or just the word assembly? Anyone heard about this word assembly? Or assembly code or something along that line? So what is assembly? From your understanding, can someone say your understanding, what do you think about the assembly? You can even say it's something I never really want to program on. It's a little bit too low level, which is totally legit concern. It's a machine language. Exactly. It's a language that somehow my machine understand. Why does the machine understand this? Once you're walking into this like area that I would typically call this computer architecture, which is basically area I'm working on primarily for my research. What we do, right? We would design both the hardware, the actual component that goes into your computer, right? How to put things together. How do we put things together and work with people who do circuits and who do digital design and make sure all the components are really, really fast. But if we don't have the way to command them, it's just a box of nothing. It's just a metal chunk that did nothing, right? So you need the machine language to be able to command from the human point of view, right? Computer are tools that we can command to do a lot of useful things, right? So what we do is the ISA or the instruction set architecture will define the list of commands that the computer understands. Specifically, this language allows the computer to know exactly how to control the hardware. The microarchitecture is basically the actual hardware that allow the circuits to perform all the commands. So that's ISA and microarchitecture. ISA is the language. Microarchitecture is the computer, the hardware. The microprocessor that you buy is a combination of both. Right? We give you the language saying, hey, if you want to command your computer, write the assembly with this format. Then once you write it in this format, the computer would know exactly how to run. Another good analogy is this. This is a language that we can talk to the computer with. So let me ask you this. Anyone here heard about the M1 processor from Apple? The one in new MacBook and MacBook Pro. That would so basically cost a lot of money in breaking the bank. So to be honest, the design is really, really, really well done. But do you know what assembly language that the M1 chip is in? Is it x86 or is it something different? It's ARM, right? ARM is another company that it's one of the company that create IPs for hardware design, including the ISA. And I'm gonna compare, like, so do you know what assembly language does the Intel and AMD chip use these days? For the Intel chip, so let's say you go to a computer store and you buy the Intel processor or AMD processor, it uses the x86. It uses the x86 assembly. So let me kind of compare this as in like, if you have a chip from Apple and it's an M1 chip, it's like they're speaking French, and the x86 is speaking Japanese. Can they talk to each other? A French guy and a Japanese guy who doesn't know English, can they communicate? With a translator, great answer actually. With a translator, they can try, right? And this is basically what's done in modern day computer. You can have Microsoft Word that works on x86. And then you have a way to translate so that it will work in the MacBook ARM M1 chip, right? So if I have a program, let's think about it this way. I have a program written in x86. So let's say it's a program written in, what did I use x86? Is this French or Japanese? Let's say x86 is using French, right? I have a program written in French, and then I give it to a Japanese person. What do they have to do to know what's in this program? Translate again, right? But you cannot directly just read the text and know exactly what it's doing. You need this translation. So this is basically the concept behind why is there an ISA. ISA is there so that you can command the computer. But because there are multiple ISA, right, and multiple different computers that use certain ISA, you need to translate them. And there was a question from section 1, which is a really, really great question, is why don't there be a universal ISA where in the future someone come up with this universal ISA and everyone would work and use this ISA? Wouldn't that be nice? So let me ask you this question. Wouldn't that be nice to have the single only one ISA that works for all the computer? So if you say no, we can. I think you're living in this country for too long. When you answer, we cannot have nice thing. Um, go abroad, and and go see how developed countries do things. We can actually have nice things. Um, sorry, but wouldn't that be nice? The answer to the no, actually, no is actually really, really good answer because I think that's true. You you cannot only satisfy all the demand with only one ISA. Because sometimes your user, with the people who use the computer would demand certain things over another. So if you want certain performance over others, you might actually adjust the ISA a little bit. You might adjust the ISA or even change the ISA, right? It's how certain language are more expressive than other language. It's kind of like if I say I want to come up with a universal language where all human can talk to each other, those are definitely great, right? There's an overhead to adapting to this new language as well, because you need to somehow build the program in this totally new universal language, which might be possible or not. Right? Sometimes you cannot afford to buy the new program. If I buy Microsoft Word from 5 years ago, right, and it used certain ISA, I don't want to buy it again. So this thing costs a lot, right? So these can kind of hinder the development of like something close to like a universal ISA. It's a good goal. It's a good goal, but it's not really achievable, right? Is it impossible? I don't think so. But it's not easy to design a good universal ISA. And then we talked about ISA already, so let's get sidetracked a little bit and go into this keyword of the semantic gap, right? The semantic gap is basically the gap between the software and the ISA in terms of the understanding of the command, right? And I'm gonna explain the word semantic by comparing and pairing up with syntax. So how many of you write C code and got the syntax error already? Anyone here familiar with that when you compile C code and say syntax error? No? Interesting. Yes, right? Because the first time you try to use a new language, similar to how I basically, if I have to speak Chinese for the first time, I'm gonna make tons of mistakes, right? No one will understand me. Syntax error is basically when you write a language, the computer, the compiler, actually, the compiler are trying to understand what you're trying to say. And it look at your statement and it's not clear. That's a syntax error. It's like it doesn't know what you're trying to do here. one of the more common syntax error that I still have nowadays is I forgot the semicolon at the end sometimes. I forgot to close the parenthesis by accident. These type of things are syntax error. Think of it in plain English, these are grammar. So if you make mistakes, the sentence would mean nothing. It would confuse people, right? So semantic is more like looking at the paragraph and try to find the meaning of it. So can I string together syntactic, basically fully correct sentence, but it doesn't have meaning in the paragraph? I put like weird sentence together, no grammar mistakes, but it doesn't have meaning. I don't understand what the paragraph is trying to say. And that's possible, right? It's possible. You can write a paragraph of English where every single sentence is correct grammatically. Putting together doesn't have a lot of meaning. It's confusing. So that's the meaning behind it, semantic. So you can have ISA with a large semantic gap where just say you write program in C or in Java or in Python, you compile into the machine language. And the machine language would resemble, instead of add, subtract, it's more like put the voltage on this wire to be high, put this voltage to be low, control this particular wire this way, connect this wire and this wire. That's a large semantic gap. It allows a lot of compiler optimization. A small semantic gap would be something that has a resemblance of a high-low language. An instruction that say do the matrix multiply. An instruction that say insert something to a linked list, right? Then you can have a lot of application-specific hardware optimization. So the translation of one ISA to another ISA, as you guys suggest already, right? You can use a translator for that. This would change the semantic gap so that the hardware designed for ARM ISA, like the M1 chip, can understand the software built for the x86 machine, like an Intel or AMD chip. So what happened if the ISA changed? When the ISA changed, the program, the binary program that are being run, the computer would not understand the compile program that are compiled by the previous ISA. If you don't have the source code, it will stop working. If you have the source code, you need to re-optimize and recompile. Compiler also have to be re-optimized for the new ISA. Fun fact, your GCC and mini compiler, it doesn't just translate your code to machine language, it also tries to understand what you're trying to do on the code and optimize that. Another alternative solution is called code transformation. Basically, you run a program in one ISA, you translate that into another ISA. Again, translator, right? So the conclusion is you don't want a lot of ISA. Think of it as a human language, right? But for the software to talk to the hardware. And you don't want a lot of languages because it's annoying, to be honest. Like you have to learn a new language, you go to a different country, you don't get the benefit of knowing the local language. It's hard to communicate. It's hard to actually convey things, right? So now that you know the existence of this ISA, or I mean, I'm sure all of you have heard about the word assembly at some point in time. The ISA basically define what is the assembly language. So let's look into what goes into the ISA. Right? The first thing that goes into the ISA is what we call instruction. If you want to command something, you need to be able to give instruction, right? For example, I can send instruction to my brain saying, go get coffee. And then I'll walk there to the coffee area in my house and make coffee. That's instruction. What does instruction have to consist of? The opcode, what are you supposed to do? Addressing mode, data types, instruction types, formatting. Basically, it has to have the definition of If the bit pattern is 111000, this is what's supposed to happen. If the bit pattern is 111111, another different thing is supposed to happen. This is how you can tell the hardware to do certain things based on the instruction that you see. Memory also has to be defined in the ISA, because when you buy the memory from the computer store, it's just a blank flat 1D space of place you can store your data, right? So the ISA would have to cover things like how are we gonna access them, at what granularity, how to manage the memory. What else? For completeness, you want to make sure your computer function, so it has to be able to handle things like what would happen if you have exception or interrupts, like someone type on the keyboard or a mouse, access control, priority, which program can have higher priority, which program would have lower priority, what's the privilege, how to deal with input and output, how to deal with threat management, who should get more assignment to each of the processor, how to control the power, and how to control the temperature, the thermal management, so that your chip are not able to grill things, right? You can kind of look it up. I'm sure there might be videos of some phones that are capable of grilling meats. And you don't want that, right? You want to be able to control the power and thermal management. You also don't, as a programmer, there's no need to memorize this at all. Each ISA would have the manual. It would tell you actually how to do things, how to organize things based on the manuals. If you do it based on the manuals, the hardware know exactly what to do. These ISA would basically, it would lay out everything that the hardware is capable of. And if you follow the manual, when you write the assembly code, it will work. The computer is guaranteed to work. I mean, otherwise you have hardware bugs. And the instruction is the most basic elements of the interface between your program, the software, and the hardware. And again, the instruction has two main components, the opcode and the operand. The opcode is basically, what is this instruction? Like add, subtract, multiply, branch, basically jump to some other location of your code. The operand is, who do you have to perform the instruction to? For example, if I have add R0, R1, R2, this is like my own make-up ISA. My make-up ISA, whenever I see this, it might mean that I'm gonna add R1 and R2 together and store the result to R0. In this case, the plus sign, that's the operator. It tells, hey, we are adding the number here. It would allow the computer to trigger the adder in the computer to add the two inputs together, R1 and R2. R1 and R2 are the operands. R0 is also the operands. The operand, in this case, R1 and R2, we call this a source operand. It's a source that generates results. R0 here, that's what we write to, that's the target operand, target and source. In many cases, sometimes we call this also destination operand or target. It's the same thing. That's R0 in this context. All right, any question before we now start from where you know C and going to where you are supposed to know next, assembly? If not, now let's talk about what happened when you run GCC, right? GCC, one of the main tasks is it translates human code, well, relatively human code in C. By this point, you probably will not call this a human code anymore, but it's a code you've written, right? So I'll call this human code into the computer language. Why is that the case? Because the processor you buy from the computer store, it has its own language. And if the two processors talk in the different language, you need to recompile into the two language. For example, if you have a binary that runs on a CPU, the same code will not, right, will not run on GPU. You have to recompile. So let's look at x86 assembly code as an example. Can someone tell me what is this program supposed to do? It should be really simple. All right, what is this program and what is trying to do? Add A and B together, right? And the result should be basically 5. You assign A to 0, B to 5, and then you add the two numbers. Let's assume we compile this into filename.o. Let's compile this into filename.o, and you can run this for sure. But to get the assembly code, you can type in objdump-s, objdump-s, followed by the object code file. You are going to get assembly. Any questions so far? Basically, if you do objdump-s, followed by the executable file, the object file, then you're gonna get the assembly code. Right? And with this, the first thing I will do is I'll put the assembly code up top so we can kind of mark things. Anyone want to take a guess what's this part I just circled? It's the int main, is your function, right? It's a function name. It's the label that mark the beginning of the function. What is 5FA? Anyone want to take a guess what is 5FA in here? Close. It's close to the line number, but if it's line number, why don't it start from 0 or some 10 or something? Remember that program is stored in the memory. Program is stored in the main memory. And we can use pointer to point to my function. Yes, this is the address. 5FA is the address of my main function. This is where my main function is located at 5FA. All right, with me so far? Now let's look at the next thing. This column here. It starts with 5FA and then have 5FB. Basically, every single line, this is your assembly code, right? This is your assembly. So what are these numbers to the left that start from 5FA and get incremented to 5FB, 5FE, 605, 60C, 60F, and so on and so forth? Anyone, how many people think these are, well, hex number for sure. How many people think that these are also addresses? These are address, right? And what are the address for? It's actually for each individual line in here. These are the address where each individual line of your assembly code are being stored. So if I somehow currently point to 5FE, which is this guy, it basically means that I'm pointing to this assembly code in this line. Move out 0, -8 RBP. So any questions so far? Because that's one thing that you might be curious about. Anyone notice that it doesn't go up by 1? Yes. Well, I mean, it has to initialize a function. It has to store like a 0 to A, 5 to B, which is basically this. This is basically store 0 and 5 to A and B. Well, it's a combination of these 4. Question. A and B increment by 1. B and E increment by 3. Anyone want to guess why from 5FB we go to 5FE? Why is the next line not 5FC? Or close actually. If you look at this, you'll see this number, right? This number. So let me clean this slide a little bit. These number are the actual bits that represent the instruction. So push RBP 55, move RSP RBP 4889E5. Move out, this whole thing is these 7 bytes. So these, the number I circle are the actual binary in hexadecimal representation that represent the assembly, that one line of assembly code. So from 5FB, move RSP RBP, how many bytes is the size of that one line of assembly? 4889 and E5, how many bytes are that? Actually it's 3 because each pair is 1 byte. So each pair is 1 byte and 3 pair for H89E3 is 3 bytes. So you would notice that from address 5FB, I need to increment by 3 so that it points to exactly the beginning of the next line. That's in 5FE. And then I need to go 7 bytes because the next line is 7 bytes long. I need to go 7 bytes to 605. So that's how you can pack your program into the memory. That's how you can pack your program to the memory. All right, everything clear so far? Well, there are definitely unclear parts that I'm gonna explain next. But for now, you now know why. Great question. This is an awesome question. When we run this program, is it going to be the same address? Is it going to be the same address? So let me go back one slide. You might have noticed I said virtual address space. Every single program uses virtual address. So the virtual address is always going to be the same. The actual location in DRAM would be different. The pointer that we use in C, it points to the virtual address. We will learn about this toward the end of this course. So bear with me for now. Just assume that every time you run this, the virtual address is the same. And every time we have pointers, it's also the same virtual address. All right, with me so far? The actual location in DRAM, that's called the physical address, and we'll learn how to change the virtual address into physical address. All right? So these again are the actual bits that represent the instruction, and this is what the computer sees. Then, what does this do? These are actually the These are the actual command in assembly that represent adding the two number inside the register EDX and EAX, and we'll talk about the register in a bit. Think of this as the variable EAX and another variable called EDX. We add them together and store it into EAX. Is the command. And the command, right, will be exactly, if you convert this to a binary, it will be 01D0. If the computer sees 01D0, it knows right away you are doing this add EDX EAX. So the one to the left is the actual bit representation of this one line command. If you change EAX into, for example, EBX, the number to the left would be different. The computer can tell the difference. And now you see multiple types of instruction. What I just show you is called a compute instruction. A compute instruction, as the name suggests, simple. It's doing some computation. Add, subtract, multiply, XOR, and basically deal with the computation of the data. There's also memory instruction that move the data in and out of the register. Think of this as the way to interface with the main memory. And again, we haven't talked about the register, but think of it as a temporary variable that your CPU can access. Register is like a temp variable that the CPU can access. Control instruction will govern things like where do we go next? Are we going to the next line, or are we jumping somewhere? When you have if else, are we running if or running else? If you have a loop, are you going back to the beginning of the loop, or are you going to the next line of your code? Right? And as I mentioned, we have this thing called opcode. So what I just circled is the operation. So these are the opcode that tells the computer what the instruction is supposed to do. What the instruction is supposed to do. The operands are to the right. These are the data involved in the opcode. Sorry, what's the typo again? The operand that tells what do I do, where is the source of the data, what do I do with the results, where do I store them. And then you also see things like an address or flat value. So this is not the address. This is basically when you have the $sign in assembly, right? This is the value. So this is basically literally value 0, number 0. This is literally number 5. And when you see parentheses, this is the address. So use RBP, the value in RBP as the address. Think pointer, right? Use the value of RBP as an address. Subtract 8 from them and store the value 0. So over here, that's the address. It represents the offset from the address of RBP. We will talk about this in more details next lecture. We'll talk about this in more detail next lecture. What's going on with this move out instruction? All right, because before we go through that, we need to know that this is also the operand, the register involved in the instruction. And because I mentioned register many times, let's define this. Register are extremely fast but tiny temp variable stored directly on your processor, sitting right in the processor. These are visible to the programmer. You can access them using the assembly. Compute instruction can directly access the value and store something, can operate on this register. And whenever let's say you read a textbook and you see the word register file, that's a group of register. It's a group of register. So you might have the question in your mind right now about then what's the difference between the register and the memory. Here are the difference. Register is in the CPU, directly in the CPU that you buy. It's defined by the ISA. ISA will tell you these ISA have these many register, and here are the name of all the register. The name are known. This is not the cache. Great question, by the way. Great question. These are not the cache. Register is even smaller than the cache. These are temp variables usable by the processor itself. They don't share across processes. Each program can access the register right away. And they're really fast. One clock cycle, you can access them. A cache would take longer. It's much bigger, but it takes longer. Most processors only have a subset number of register, like 16 register, 32 register, depending on the complexity of your CPU. So register are tiny, really small, but really fast. All right. The memory is huge comparing to register, right? You have gigabytes of memory. Access to the memory requires actual load and store instruction. The memory instruction is required to access data from there. It's extremely slow compared to register. Typically, going to the memory takes 12 to hundreds of nanoseconds. That's between 50 cycle to 200 to 400 cycle, depending on many things that can go on. Comparing 1 to 50, that's already 50 times faster, right? And memory, because they're big, they can be shared across different programs and processes. All right, so hopefully it's more clear now. Register is programmable through, where you can interface with them. The compute instruction can do something with the register, and it's fast. It's in the CPU itself. Basically, when you buy a CPU, it's inside the processor. The cache is outside of the CPU, but on the chip, right? It's on the chip, but it's not inside the CPU. The register is right there, integrated with the if you kind of abstract away the chip design, it is integrated into the processor part. Then there's also special register, and one of the common ones is called the program counter. This is a special register, and it points to the current line of the program we are running. Why do we need this? So that we can tell this is where we are. If we go next, this is the next line that you have to run, right? Basically, this points to the current assembly instruction we are running. And program is data, right? So the program counter is pointing to that data. And typically this program counter is incremented every cycle. Why? So that your program can proceed to the next instruction. Except for when you have code branch, in that case, you would jump somewhere, if else or loop, right? If you read textbook in computer architecture or basic kind of like computer engineering book, sometimes this is called instruction register, same meaning, exactly the same meaning. And to move the program counter, so let's say my program counter is 605. Right now it's 0x605. What instruction am I running? Almost. The 5FE, it was the previous instruction. The current instruction is that this move out, this one, right? And then when I finish, what should the program counter be? When I finish this line, what should be the value of my program counter? 60C, right? And if once I finish this line, what should be the next value? 60F, right? So this sounds kind of trivial, right? But it actually gives you so much benefit. Can someone tell me what's the benefit of being able to keep track of what's the current line? So why do we need this? Do we need this? That's actually one of the benefits that we are not going to cover in this class. It's more advanced. When error happen, what do we do? But so great answer. But the first basic thing is so that we know what line to run next, right? So basically, the computer is not magic. You can't just say, hey, run this program, and it can keep track of where we are. There are hardware components being put in to make sure we know where we are, and that hardware is the program counter. When error occurs, let's say you have an exception, program counter would be stored so that you know if you want to resume execution, it follow that point. This same thing also would apply to when you have multi-threading. When you have multiple programs running on your computer, it can keep track of what's the program counter. Another great question. Does it not increment by increment uniformly, as in like add, maybe always add 4 bytes, 4 bytes, 4 bytes, 4 bytes, something like that? Yeah, that depends on the ISA. So this is the property of the ISA. So let me go sidetrack. And this is a little bit more advanced. We cover this in the next class for the complex arc, the class after this. So the ISA, some ISA require every single instruction to have these many bytes. For example, if you look at another popular ISA called RISC-V, anyone heard about this before? RISC-V is a free and open ISA. If you want to do research on ISA, it's one of the good ones to try, because they're free and because they're really, really well designed, actually. RISC-V dictate that the instruction has to have certain number of bytes. The 32-bit version has 4 bytes. So every instruction, PC go up by 4 all the time, because you guarantee that it is going to take 4 bytes. x86, we call this a variable length. So this is a fixed length instruction. This is a variable length instruction. So in x86, you need to figure out what's the next PC. It actually have to, like, by design, to update the PC, x86 is going to be a little bit more complicated, because you need to figure out, okay, do I add by 3? Do I add by 7? Do I add by 2? Do I add by 1? There are multiple steps to trying to figure out how many bytes do I add. Exactly, yes. So that's the benefit of variable length instruction. It's much more space efficient in some cases, right? Why do you want the program to be small? Anyone want to take a guess why sometimes we might want our program to be small? So how many people program in Arduino or like a microcontroller before? For example, the microcontroller that go into this remote for my air conditioner. These things have such a small. Actually, if you want to try, you can buy this microcontroller and actually program them. I think the kit would run like a few $100, maybe a few thousand at most, and you can try to program them. The microcontroller typically come with a really, really small memory, which means that your program had to fit in that small region of memory, right? So that's why somehow you want the code size that are small. Another benefit of x86 variable length instruction is, if you want to extend the ISA, you want to add more and more instruction, I guess you can also keep adding, right? Because the instruction can go to infinite length in theory. So you can keep extending this. For the fixed length instruction, there's a limit into how big and how many instruction there should be. That's it for the class today. This is great. There's so many interesting questions here. More time. Yes. So that's the downside of the variable length instruction, because you need to figure out, if I need to update PC, I need more logic to figure out, do I update by 3 or 7 or 5, right? It's more time consuming, because you need to first figure out, okay, do I fetch 1 byte or 3 bytes or 4 bytes, right? I mean, for example, let's say I'm at 6OF, right? At 6OF, how can I tell, do I get 1 byte from 6OF, or do I get 3 bytes from 6OF? Because in this case, we need 3 bytes and exactly 3 bytes, right? So you need to build the hardware to figure it out. And as you suggest, it's more time consuming. It's also more complex to design, right? In a fixed length instruction, it's simple. You know, okay, it's 4 bytes for sure. I'm gonna take out those 4 bytes and look at them. All right, any other questions? All right, if not, actually, that's the end of the lecture today. Next week, we will continue on with actual assembly. So we'll expand upon what we see today and talk about what are the different instructions you can use to program in assembly. We are not going to ask you to program in assembly. I can guarantee you that. But we might ask you to fill in some like some line of assembly and say, oh, what's going on in the in-class exercise. All right. There's no in class today. It's a quick note. I have made another mistake on your exam. For this, the last question, if you did unsigned long already, feel free to keep that. It's fine, and tell me how big do you assume for the unsigned long. But my intention, I'm sorry, I'm supposed to write unsigned short star C. So I will take both versions as a correct answer. All right. So that's one of my announcement today. The rest will migrate to Discord. If you have any question, I'm gonna be there and answer any question from the exam, as long as it's not Ajahn, what's the answer for this? All right. So we're done for the lecture today. We're gonna migrate over and we resume with the Q&A for the quiz. And also the assignments as well. So basically, whatever you want to ask, we can ask now. There's no in class today because I want you to make sure we have the zip file already. Well, okay, so that's a great question. So for the exam, if you put the answer in the PDF, the only question that I would like the code is the second question, and you can zip them. You can just upload individual file, both works. Actually, to be honest, Canvas would zip them anyway for me, right? So either way works for me. All right. And my PowerPoint just crashed.